So welcome to Lab 5. Today we'll be going over two notebooks. One is the MNIST digit recognizer and the other one is a classification task on the Wisconsin breast cancer dataset. So to begin with, let's download this folder Lab 5 from Hands-on Labs and Solutions on our course portal. Unzip it next to Lab 3 and 4. It has all its dependencies, so it will work fine without any additional notebooks from the previous labs. So if you've downloaded it, we can start with lab. We can start with the Wisconsin breast cancer dataset. Okay. So the goal of this data set, the classification task, is to find so there are a lot of variables in this data set, right? There are many variables that kind of help you predict if the cancer is malignant or benign. So that is the goal of this. That is this data set. So based on certain features, we wish to predict if the cancer is malignant or benign. Okay, and we also want to know what are those features that strongly affect this classification, right? So those are the main tasks of this notebook. But for neural networks, we are going to restrict to finding a good accurate model and not go much into the other methods that we use classification. So again, we start by importing all the necessary modules and libraries. Okay, so this data set has 10 real valued features, one for each nucleus. Okay, and the attributes are radius, texture, perimeter, area, smoothness, compactness, concavity, concave point, symmetry, and fractal dimensions. And now there are three types of cells, three types of cell nucleus. So we'll see that too. So there are a total of around 30 variables. Okay. Yeah. So to begin with, we do an exploratory data analysis. So we start by loading the data. Okay. And we say data.info, and then we see how our features look like. So what are they? So so we did have these 10 features. Now they repeat for three different types. So one is the mean, one is the standard error, and then the worst. So sorry, these are not the different cell types, but they are different statistics, right? So we have this information, and there are 30 of them. These are the 30 features we have. Next is we see that the data type of every column except diagnosis is float 24, since each column is a measurement, which is they are numerical variables. Let us take a look at the column unnamed 32. So unnamed 32 is there's nothing in unnamed 32, right? It's just these are all NaN. So we can remove this feature, and we can also remove ID because ID is not required for our classification. It doesn't add any meaning to as a feature. So we remove both these columns, okay, and we just drop them in place. So these are all some pandas related syntax. So so in this we just drop these columns, okay, and now we describe these columns. So this is again, these are all pandas syntax. So what we do here is we want to see some information, some descriptive statistics about each of these features. So we start with count. So there are a total of 569 values in this feature. And then there are two unique values, which means is it malignant or benign. So this is a target variable. Okay. And then it tells you, since it is treated like a classification, categorical, it it just tells you what is the top value and then what is its frequency. Okay. For the others, these are all numerical variables, and therefore unique top frequency is not shown, but rather what is the mean value, what is the standard deviation, min, max, and then some of the quantiles. Okay. So we have this information. So we do see that everything shows 569, which means there are no missing values. So that's pretty good. Okay. And we have one, and we don't have any other categorical variables in this data set. Okay. So these are things that you will sort of need to work with when you are working on real world data sets. They're not as clean as toy data sets, right? So we do notice that all of them are numerical, so we don't have to do any label encoding or one hot encoding. So okay, now let's just take a sample, data.sample.transpose. In the sense, I take 5 different samples and then 10 different samples, and then I view them again in the same manner, just to see, okay, how does it look. So we have M for malignant and B for benign. This alone, I think we will have to change into 0 and 1s, because we want our target variables to still be numbers and categories instead of letters. So let's do that. For the next part is we do missing value analysis. We see if there are any missing values in this data set. And then it turns out that there are none. So that's good. Okay. And we also see under data.diagnosis, we see what are the unique values that we have here, and they are malignant and benign, and they're of type object. So we'll have to change that. Okay, so data imbalance check, we see how many values of malignant and how many values of benign tumors do we have. So we have around 212 out of the 564 or so number values. 212 are malignant and the rest are benign. So we observe that the data set consists of more of benign tumor diagnosis than malignant tumor. Any classifier must do better than the baseline prediction of 357 by 579. Okay, so what this says is that, okay, if I just I see that benign is the maximum. I mean, it's the largest category among these two, and any test data sample I get, I automatically just classify them as benign, because they seem to be the highest. They seem to be the maximum category here. So I can do that, and that is a baseline prediction, and that should so that is 357 by 579, right? Kate, do you want to say something?
Yeah, that's baseline. I think it's also called the 0R when just looking at the data and not even any predictors, right?
Yes.
It's another
Yes.
term, that's all.
Yes. So so that turns out to be 63.4%. So we need to do better than that, because that is just classifying very basically, right? So that's the 0R classifier. Okay. So then what we do is we first of all we map M's to 0 and B's to 1. Okay. So this is a way of one hot encoding. It's a simpler way using map. Now, for the next part, Okay, have I been running this notebook? I don't think so. Let me run all. Okay. So the first thing we do is we separate our features into the features means, feature standard errors, and feature worst. Okay, and then we compare them amongst each other. This is not necessarily, I mean, we could compare all the features together, but then you see that we have 30 features, and comparing all of them together, it is a lot. So we kind of separate it into groups, and then we analyze them. So here what we do is, okay, this is some panda syntax. We melt the data frame in order to easily visualize. Okay, so these are not necessary for this notebook, but yeah. Okay, so now what we do is, a violin plot sort of, it is like a histogram, but then it's like a smoothed out histogram. And this is one type of visualization where it's kind of easy, it's easy to the eye to see the distribution of the data. Okay, this basically tells you how the data is distributed. And now the thing to notice is that 0 is malignant, and 1, wait, sorry, 0 is benign, and 1 is malignant. I think that's how it is in the, that how I coded it? Oh, sorry, no. What I have done is I've done malignant as 0 and benign as 1. Okay, so which means this orange color, that is malignant tumor, and this is benign tumor. So this kind of shows you the distribution. Okay, and it tells you, for radius mean, if I kind of separate out my malignant tumors and benign tumors, okay, based on malignant and benign, and then I plot its distribution. Okay, radius mean for malignant and radius mean for uh, benign. This is how it would look. So it kind of like it's mirroring this distribution on top of each other. I mean, side by side, and then we're comparing how they're distributed. So this sort of shows you that in case of radius mean, uh, the mean of this distribution is well separated from the mean of this distribution. So we do see that several of these variables have that. Several, for most variables, we do see that there's quite a lot of separation between um, malignant and benign. So maybe except for this, which is fractal dimension mean, we do see that it is not, this feature is not actually helping you much, right? It's not actually telling you a lot about a lot of difference between the malignant and benign tumors. So this is one thing that we do notice here, and uh, that's why it's good to visualize your data and sort of understand it, right? So
Um,
yeah.
I am not understanding. So, given that the means are not centered, for example, the first one, what does that really mean, though?
What it means is that when you plot this data, right, when you, for example, if you do a scatter plot, which I have not done, what you would see is that there is the there are points, like if you make a scatter plot, the red, the malignant tumor points would be well separated from the you know from the benign
Got it.
tumor.
Okay.
When you have radius, in this case, what actually the point is, you cannot make a scatter plot against say 0 and 1. So what this would look like is, this would look like a line. Okay, and then um, you'll have some points on 0 and some points on 1. Okay, and then you plot the radius mean for all the points that, for all the data points that have 0 as their what to say, diagnosis, which is like 0 means here in the case it's malignant. So what it look like is like you have 0 here, and then you'll have 1 here, and then you'll have like a line on which you'll have a lot of points jumbled up together. And what happens is if you draw the distribution of those points, that's what this looks like. That is what this shows. Does that make sense?
So what you're saying is that the orange line on this radius, what you're saying is that it's going to be appearing on us one straight line, and that too not in a like it's like a curve equal to x equal to, let's say, 1, right?
Let me just I wish I can draw it somewhere. Wait, let me, yeah. Okay, so what it would look like is you'll have say 0, okay, and then we have 1, okay, and now on this axis I'm going to plot my radius mean, okay, and this is going to range from some number to something, okay. And now if I plot these points, because I'm going to plot them like this, and then they're going to be on this line, okay, and I'm going to plot some of the benign tumors here. These both come from the same variable, but I'm just splitting them according to their tumor, okay. And now when I plot the distribution, this happens. They have a different distribution, which means malignant tumors have larger radius and benign tumors have smaller radius. That's what it means. Does that make sense?
Yeah,
It's a nice sketch.
So
Yeah.
So Kyle, why do you have to build this complicated violin-like thing? It's very straightforward, right? The larger the tumor, the larger the radius, more
Yeah, this
chance,
is, you
that
can
it's going to
compare
be.
them, right? Like, how else will you compare these things? Like, what other plot can show you the separation?
A simple
This is
bar would
one.
tell, right?
Yeah,
It's
this
not,
this
yes,
would also,
yeah. So
yeah,
that looks
this
better.
will also.
Yeah. This is easy. This is easier to tell.
Okay.
I don't know. It's
Okay.
maybe that looks more jazzy, but once you kind of went in deep, then I could get it. What is going on, right? So
Okay.
yeah.
Okay.
But it's yeah. Now that when you explain it, then it makes sense.
Yeah, this does explain it, but once you understand the plot, you can quickly understand it from here, because here, okay, how do you, you do see a well separation between these two, but this is like easier on the eye. Is what, once you understand what a violent plot is, it's easier to understand. But yeah, so this is the other way to represent it, where say for radius mean, this is a box plot, okay. So this line shows you the mean of the benign tumors, and this is the mean of the radius, malignant tumor. And we do see that for each of these variables, it is again, it shows the same thing, but it shows in a better way, I guess, like Albert says. So they are well separated, and then we do see that so the top and bottom line, they show you, this total uh, box, it shows you 50% of the points, the central 50% of the points, and these lines show you the remaining 50%. Okay, so we see that
What are these rhombus on top of them?
those are outliers, points that are like further away.
Okay. So the end of that line, right? Is that like
Mhm.
the last item, or so you
Here.
said like box is the 50% of the center population,
Yes.
and then
Yes.
what is the remaining line?
This shows you the last 25%, and this shows you the first 25%.
So that
Okay,
that
and
should complete the 100%, right?
that should complete. But what this software does is sort of if it stretches it till here, it doesn't make sense. But these are where most of the 25% of the point lie. Okay, and then there are just four additional points that are further away, and there's no point in like stretching it till here. So this is where majority of the 25% of the points lie, and then there are a few more points additionally outside.
So Kyle, to what Abhishek was saying, right? So if you
Uh-huh.
take the red box, the total
Mhm.
line from top, including the outliers,
Mhm.
so that is the whole total of all the points.
Yes, that is that's 100%.
So and then you have the mean dimension of benign ones is in that box, and the remaining ones that are not benign are in the blue box. Correct? Or am I kind of?
Yeah. Okay, so
So why?
this total is like 100, like for concavity means this is like 579 points. Okay, and then here we show some I think this is like 200 points, and this is the 300 points, the remaining 300, which are uh, these are benign tumors, these are malignant. So uh, Albert,
Yeah.
is there anything else?
Yeah, I think that's clear enough. Thank you.
Okay. Okay, so we do the same for the standard errors, and then we see how well separated they are. Okay, let's look at the box plots. And this one is not as separated as the one we saw before, visually. Okay, and similarly, we look for the worst features. Okay, here we do see a lot of separations, right? So again, so yeah, we plot the box plots, and then we do see separation. So what we get from this analysis is that not just one, but almost all of the features tend to separate out the data set pretty well. Okay, right? And now, what combinations of them should we choose is the question. And uh, do we choose all of them? Does each of them separate the classes to an equal extent, or to what extent? Okay, so those are some of the questions that we should have in mind when we go forward. uh, so okay, next is we do a correlation study. Okay, and what correlation does is, okay, so there are 30 variables or so. I want to see how correlated these are. I mean, they must be, right? We look at it, and we do see that they seem to separate. For in this case, in all of these cases, we see that malignant seems to be having a higher radius, larger texture, I mean, more texture, uh, more parameter, I mean, perimeter, and a lot of, I mean, larger area. But these must be correlated, because if I have a larger area, then that automatically means that I also have a longer perimeter, right? So these must be correlated in way, and similarly radius must also be larger. So therefore we should see some correlation between these variables, and that we should note down before we move on, because um, because that that's the case of multicollinearity, where we have variables that don't give any more information than the others. We can just remove those variables that, if for example radius mean kind of explains instead of perimeter and area, I can just choose radius instead of having perimeter and area, right? So they don't add any more value to the model. So for that, what we do is we do a correlation study, and a correlation is like, if I have correlation 1, which means uh, both those variables are exactly the same. If they are somewhere in between 0.75 and minus 0.75, they are correlate. As we go from 1 to 0, if I am at 0, then I'm sure that okay, there's literally no correlation. And and then again, if I go to -1, which means that um, those two variables are negatively correlated. As in, for example, as I increase the radius, the texture sort of goes down. That's not the case, but that's one example. So okay, so we view this plot and then we see these colors. So this means that it's highly positively correlated, and we go down, this is highly negatively correlated. So both these colors um, you know tell us that there is some sort of strong correlation. So so we look for those values. We look for something that's like really black, and then we look for something that's like really white. I could have used some other um, you know uh, color scheme here, which would be a divergent scale. That would have actually helped. So I'll make that change so that we can better visualize this part. Okay. So here we do see that there are perimeter and perimeter mean, perimeter worst, area mean, perimeter worst. So these points, these two say these two features seem to have high correlation. Similarly, radius worst with perimeter mean, radius worst with area mean. So all these sort of are correlated. So we do know that, right? Like the cancer is not like exactly spherical. So radius worst is like the worst radius. So, and that sort of influences the mean area. So
Kyle,
that
whatever
Mhm.
is red means it is a cancer cell in this whole, orange.
Sorry, can you repeat again?
So you see the color combination, right? So
Mm-hmm.
the orange means, is it cancerous? Is it positive?
No. It only means that there is high correlation between two variables. So this doesn't tell you anything about the cancer, because this just tells you the correlation between two variables. So area mean is one variable, radius mean is another variable. Are they two correlated? As in, if I increase radius, will my area increase by, and is it like completely influenced on the radius alone? So this is what correlation tells you, right? So it does look at that. Area mean and radius mean, they are highly correlated.
Okay, so the color means nothing here.
The color, what it means is how correlated are they? That's what it means. So if it's 1, it's like whitish in color. The correlation is like really high. If it is black, then it's like totally negatively correlated.
Okay.
So okay.
Thank you.
So we do see that there are a few variables that are correlated like that, that have really strong correlations. So we've seen this visually. Let's go and like look at the correlation numbers, and then just highlight the ones where there is the absolute value of the correlation is more than 0.85, which means that the correlation is less than minus 0.85 and greater than 0.85. Okay, so we look at that, and so I've highlighted those. So obviously, along the diagonal, the correlation is 1. That is because diagnosis and diagnosis is definitely correlated, right? If I increase
So,
diagnosis will increase. Sorry?
a variable is always going to be very highly correlated to itself.
Yes, yes. So that's the thing over here. On the diagonal, that's going to be the case, but let's look at the other ones, and we see perimeter is correlated with radius mean. So there are other correlations as well. Okay, so I've noted these things down, and and I'm removing them. I'm removing of not both of the correlated variables. I remove one of the correlations, right? And then so therefore I've removed a few of the variables that I think are not required for this state for this model. Okay, so I've removed them, and as the next step, I am going to do some standard scale. I'm going to scale my data. So the next point is to visualize it along. So this is like what some I've removed some 8 variables here. So I still have 22 variables left, and which means my data has 22 dimensions, and it's very hard to visualize in 22 dimensions. I would want to bring them down to 2 dimensions and visualize it. In order to do so, we do principal component analysis, right? And principal component analysis just tells you, it just gives you, say the first feature tells you along which axis, if I slice my data, will I see the maximum variability, right? So where does my data vary the most? In which axis does it vary the most? So if I take the first 2 components and I do PCA, I see something like this. So now this axis is not just one of the features, it is a combination of the features, right? And in some multiplied by some scalars. Okay, so these are basically the first eigenvector, and this is the second eigenvector. Okay, and so this is how my data looks. I have not added uh, the labels. Sorry about that. So one of them is malignant and the other is benign. Okay. And this is like, I have not done any other processing. I'm just viewing the data along its principal components. And already I do see that there is like almost a line that can separate them. I mean, not completely separable because there is overlap, but I still can draw a line, right? You can visually see the line that could be drawn. And this is what we will be doing. Okay. And now we also see how many principal components kind of explain explain the separation. Okay. I see that around 1, 2, 3, 4, 5, 6 components, says 6 of my principal components explain about 88% of the variance in the data, right? So from then on, the contribution of each other component of the remaining variables, principal components is less. So these explain a lot. So we can probably use this for our model. You can try out things like that. So for my neural network model, which I'm going to train so that it can distinguish between benign and malignant, I'm going to transform my data into principal components and then apply the model, which means the first it will still have 22 features. Okay, you can probably reduce the number of features to 6 and try it out as well. It will have 22 features, but the 22 features are all principal components. Okay, so yeah, so here I'm importing things for my neural network. And this is just you'll see why we do it. Okay, I'm going to save, if if I'm training my model today, I want to save the model so that I don't have to retrain the model again and again. So I'm going to save it with a date and a number. Okay, this is for that. Now I do the same thing as before. I load my data into simple data set, okay, which is a PyTorch object. And then I divide my data into train and test. Okay, and so I train with 80% of my data and I test with 20%. So, and also I randomly select. So I randomly split. I just don't split like first 80% is my training set and the next 20 is test. I randomly select them. Okay, so 455 examples are for training and 114 are for testing. Now I print out just one value of the first value of my data set. Okay, this is the complete one. So and then what I see is that I see 22 features. Okay, and this is the feature vector and this is the label. So the label is 0, which means in this case it is cancerous. This is the malignant tumor. Okay, so here I'm going to set some hyperparameters for the model, right? So and then I've highlighted these points that you can modify these things, right? What do you have to modify? Wherever you see these arrows, you modify them, and then you try with different values of the hyperparameters. And yes, so when you see the in features, now it must be 22, right? There are a total of 22 in features and there are 2 out features. And why is that? Why do we have 2?
Malignant and benign.
Yeah, right. So we want to classify 0, 1. So that's why we have 2 of the out features and 22 in features. Okay, so I start by just give the batch size is 1, which means each training example is trained 1 at a time. Okay, and I am going to comment out this part and I'm going to train with uh, just one, with an input layer and an output layer alone. So we know that this would just be a linear classifier and this would just draw a line between the 2 features. Okay, so let me train this. Okay, so this cell is just for you to set your hyperparameters. Now we train our network here. Okay, so there's another option which I will explain after this cell, is to like load your saved model and then train it from there instead of setting new hyperparameters every time. You might have found a good model that works really well. You might want to save it and then reload it and try to improve it further. This is for that. So here, okay, I'm training my model and I've just taken 10 epochs, so it's gonna be fast, and it's just 2 layers. So okay, so and my score function is accuracy here. So accuracy sort of tells you how many points are classified correctly, right? uh, so that is kind of like my metric here, and I'm just seeing how many points have I classified correctly. I seem to have classified 98% accuracy in training, but that is definitely not what we want. We want to see in the test accuracy. The test accuracy seems to have converged, so it's not improving any further. Maybe if I restart the algorithm, it's going to start from a different point. It might converge better. So that's something you'll have to test. In this case, the best I could do is 95. But is 95 good enough to classify between malignant and benign tumor? is probably not. We want to be really sure, right? And probably accuracy is not what we want to measure with. Right? There are other metrics which we will learn in ML-100. So in this case, I've just used accuracy. Okay, so this part is to save your network. So I'm creating a dictionary checkpoint, okay, and I'm going to pass in a few of the hyperparameters that I've set, which is the epoch, and this is the model itself. I'm saving the model, I'm saving the optimizer, and if I'm using a scheduler, I'm saving the scheduler. Okay, all this to train again in the future. But if you want to test again in the future, you can just say you can just you can just use this part. But since I'm assuming that I will train this model again in the future, I'm saving all this information and also the results. Okay, I'm saving it as a dictionary file. Now use torch.save and then save it as a pth file. Okay, so and then I've already set the path in the first cell, right? So I'm just using that path. But and after I save it, I'm updating my index to I plus 1, and then I change the path again. Okay, so that every time I train a network and I feel like saving, I'm going to save a different file, and it will show up. It will show up here. So I've trained all these models, and they've been saved here. Okay, so now I'm visualizing. Okay, let me visualize this. So this is actually not better. The one before was much better. So this has a lot of ambiguity. Okay, so what does this like background color mean? So when I say when it's like dark red, it means it's like very sure that it is probably this is malignant, right? Yeah, this is malignant. 0 is malignant. So this is the model is very sure that the the data point corresponds to a malignant tumor, cancerous tumor. But as I move towards this sort of place where there is a lot of intermixing, the model is less sure where which side should I classify the point, right? So along this particular line, it is like 50-50. It's not really sure where to classify. But as we move again to this side, we see from white it slowly becomes to light blue and then dark blue. So here it's like very sure. It's sure that it is a benign tumor. But as we move to the center, it's again not very sure. So that's what this sort of this contour shows you, right? And if you worked on lab 4 or lab 3, you would see these, you would see this like probably even more. Here it is like kind of sure. It is pretty good. But if the last time I ran the same for the same setup, I think it was better. Right? Okay, so this is just a linear model. I tried with this model, and this model had a better accuracy, and this sort of this ambiguity was lesser, which means it was dark blue till here, and then only a little part of it was white, which means the model was pretty sure of what it was doing. So after after we go through the MNIST digit recognizer, you'll have time to play around with this and find better hyperparameters, right? And go over this code as well. So this comes to the end of this notebook. And yeah, one more thing, you should also note that I visualized it in a lower dimension, right? This is in the first two principal components, and to facilitate that, I've chosen these points on the principal component axis. The way this has been visualized is I've chosen points on the on these two principal components and kept the rest of the components as 0, and that's why I'm able to visualize it like this. So that's also something to note.
So just wondering, like, how this principal component to like the formula you have, like some 22 components are combined into one principal component, right?
Yes, yes, you can. Yeah, I can print that out. Say PCA dot. Uh, wait a minute.
Components and
Just components, and I think there's one underscore after it, right? PCA components. Yes. So this is the first component, and it has like 0.2% of the first variable, 0.1% of the second, 0.1. I mean, not exactly percent, but you know, the values. So this is the first eigenvector, first principal component. This is the second principal component, and then so on. We have 22 of them. Abhishek, does that answer your question?
Yeah, means I got like so each the first component is have around like how many 22 okay, these are 22
Yes.
variables, so all the 22 variables are combined into one principal component. And but so what does these 22 principal components represents?
They are in some combination of the 22 of the original components, 22 of the original features.
Okay, so what I'm understanding is that this first part which you had highlighted is the PCA1 or principal component
Yes.
1.
Yes.
And we are drawing the graph between PCA1 and PCA2.
Yes.
So what are the remaining ones, and what's their significance, or what is the significance of
We're
each?
using them for visualization. In this case, I'm using it for visualization because this is where I see the maximum variability. I could also plot between, say, radius mean and area mean. Okay, let's just you can try that out as an exercise, right?
No, that part I understand. Like if we will choose two different variables, the line might not be straight. But is this the
No,
PCA?
it will be straight there too. It will be straight there too, because the model is linear. The only thing I'm doing is I'm just like rotating my axis. I'm rotating my axis to a different orientation where there is like maximum variability of my data. So the significance of the first component is that this is where my data varies the most. Okay, and when I draw a line here, it makes more sense because now I can see a lot of variability in the data, right?
Okay, so yeah, so PCA1 is so we have like tilted the plane in such a way that
Yes, we are making
these
a
2 points are
slice.
most
Yeah.
distinct. So
Yes,
then what is PCA2?
it is the along. This is another direction where it is. So PCA1 is shows the maximum variability. PCA2 shows the next max, like the second maximum.
Okay.
So and then so on. So if you see this plot over here, so I see that first
Oh, perfect.
principal component
Yeah.
explains 30%, around 35%.
And we have taken
Yeah.
6.
No, we have taken all of the principal components. I mean, that is not how, if you're doing principal component analysis, you will probably take first 2, 3, 4, 5, and then so the till it takes up to 90%, and then you do the analysis, right? You just use the first 6 components and throw away the rest and work with this. But in this case, I've used the entire data set, like I mean, all of the 22 of the principal components. What I'm suggesting is try with just the 6. See, using all the principal components is same as not using principal components at all. It just means I've just rotated the axis in a different way, and the model is going to output the same results, nothing different. Why I've used principal components in my model is like why I've trained my model on my principal components is that I can visualize it later easily.
Just to add, it even reduces your feature space. So here, each component will give you the direction and magnitude of each feature, how important it is. So each component becomes a, when we do PCA, each component's magnitude, like how important it is. That is how when you do PCA1, when each feature's magnitude and direction is represented. So suppose it's 1.2, then the first feature has 1.2 magnitude, that much importance, magnitude in the sense that much importance in this, when you take this slice of data or this eigenvector. So it depends on, it's in that feature space, this feature has this much importance in simple English, if I have to tell you. So there are different two combinations of it. That's what PCA, and when you see the first visualization, PCA1 and PCA2 gives you some clear what to say, distinction to draw your linear separator. So that's why you use it. Our main aim is to separate it, right? Yeah, so that's how it works.
So like what
Yeah,
Harini is saying, the first principal component, it has a magnitude 69, which means it's sort
that's
of
how important
stretches.
it is. Stretches,
You can consider it as importance. So the first principal component is higher 69, and then it keeps reducing, right? The last component not very significant.
Okay.
So Kayal, you are multiplying by a tan h to get this number of what is important, what is not? Or am I?
These are the singular values. I mean, eigenvalues.
Okay, there's no transcendental
Nothing.
functions that you multiply with to get that particular uniqueness.
Different than activation function.
No.
Okay. These are just the. So
these are
this is singular value decomposition.
These are eigenvalues.
Okay.
So yeah, you are basically like decompose. This is singular value decomposition where you decompose your matrix, your covariance matrix, and then you sort of get this eigenvector and eigenvalues, right? The eigenvalues tell you how much in the first principal component you stretch your data, right? So I mean, it's sort of that linear algebra thing. So let's not go too much into it, but we can understand that this sort of tells you the importance.
Yeah. Actually, there's a video on PCA by Asif sir. You can watch it if you guys, I think then he explains it in more detail.
Okay, thank you, Harini.
Yeah, it's in ML-100, but yeah, if needed, I think you guys can access it and have a look.
Can you put that on Slack if you don't mind? So we can.
Yeah, I think one of us will put it and you can go through that. And previous students, whoever have done ML-100, I think you can just recap. I think then once you see the diagram, if you guys remember, it is that, it's the elliptical and how the points are distributed in that ellipse. Yeah. So you can just see that. I think once you see that, you might remember it.
Okay. Any more questions? Okay. We'll take a 10 minutes break and we'll do the digit recognizer. Okay,
Okay, I'll pause.
sounds good. Yeah. Okay. So the next notebook we're going to go over is the digit recognizer, and so this is a top application of neural networks in computer vision. So here we train a model to recognize handwritten number digits in the classic MNIST dataset. Okay. Um, so we start by importing all the necessary libraries and modules. And similarly here too, we are going to save the model. So that's the thing. Okay. So one thing before I want to go forward is every time you run a notebook, please set this to false. Those who don't have LaTeX, I think Manish, that should solve your problem. And if you don't have CUDA, please change this to CPU. Okay. When you run this notebook, you might face an error if, I mean, both these notebooks.
So this has to be set to false, right? The text dot used.
Yes.
Right. I did that. And also I did the CUDA to CPU.
Mm-hmm. And still you're getting an error?
So I think I did still get the error, but the last change that you sent me, I haven't done that yet.
Which is this?
Which I already did. Yeah. I think.
Okay. Okay, try running the notebook from the beginning, because I think that was a tech. Okay. Okay. I think even let's even Kate, I think she got the same error. Okay, we'll go over it after the end of this notebook. Okay. So let's start with the importing and exploring this data set. So this data set is available with sklearn. So we're going to just use sklearn's data set okay, library, and then so sklearn library, and this is the fetch openml and load digits. So load digits is your homework. Fetch openml is what we're going to do. So this is a so in this data set we have around 60,000 examples for training and 10,000 examples for testing. So in total we have 70,000 data points. Okay. It is a subset of a larger set available from NIST. So we are going to use the mini NIST, I guess. So the digits have been size normalized and centered in a fixed size image. Okay. It is a good database for people who want to try learning techniques and pattern recognition methods on real world data while spending minimal effort on pre-processing and formatting. Okay. So they've done all the pre-processing for us. So all we do is we say fetch openml, and we're going to get this MNIST 784 version 1 and return x, y, true. So this argument is to make sure that what is returned is not in a single, say, data frame. We want it separately, x and y. And also when you say return xy, this is automatically returning a data frame. Okay, so it's returning. Yes, Kate.
No, it's fine.
Okay.
That's probably a cleaner way to do it than converting the entire array to a data frame, pandas data frame.
Yeah. So return xy equals true, and then this is a series. Of course, this is going to be a single. It's going to be a single column, right? So where we look at the types, okay, what is being returned, we check that it's a pandas data frame, and then this is again a pandas series. Okay. Now we also check what is the shape of our file. So it's 70,000 by 784. So what is this 784? It is the pixels, right, in the image. So this image is a 28 by 28 pixel image. Okay. And there are totally 784 of them. And we see a lot of zeros here. So we see, okay, what exactly does mean? And so I'm viewing the first 5 values, and so we see from 1 to 784. Okay, pixels I have So this is the dimension of the data frame. So it says that, okay, this data frame has 784 dimensions. Okay, that's how we should see it. And there are 70,000 data points. Okay, so the first thing we do is, okay, let's visualize this image, right? So given an image data, so we're going to use the plot plt.im show. Okay, we're going to view the image. And also we note that this is in a single, it's like in one file, right? It's 1 by 784, but our image is 28 by 28. So we're going to reshape our data, our example to 28 by 28. Okay, and then we're going to use CMap gray because these are all grayscale. And and I'm, okay, this 2 by 2 is probably too small, but yeah, you can see it here. You see this is the number 5. And so yes, so so example comma label, this is my example, and label is this corresponding label, right? Which is in Y. So Y has all my labels and X has all my features. So I'm just I'm just uh, saving them in these variables, and then I'm using that as my title here. So title is 5, and this is its label. So this is the feature. Okay, so how does one example look like? So this is what it looks like, right? So it has 0 and then up to 250 or 256, sorry. Okay, so um it tells you how bright a pixel should, light up. So 0 means the pixel doesn't light up at all, it's 0 0, and 3 lights up a little bit, 18, 126, 253 light up like almost full. Okay, so that is what makes up this image. And so in numbers, this becomes a vector, right, of 784 dimensions. So that's how a single data point looks like. Now, okay, let's visualize this data set. Again, this data set is in a really high dimension. It has 784 features. We want to visualize it again in a lower dimension. So to visualize in a lower dimension, we use TCA, right? So we visualize along the, in this case, I'm going to visualize along the first and second principal component, also second and third principal component. So I'm going to take 2 slices on my data frame, on my data set, and do them. So before I do that, I'm obviously going to scale my data, right? Also, I'm not going to visualize all the 70,000 points. That would be insane. So I'm going to visualize randomly pick 2,000 points from my data frame and then visualize them. Okay. Similarly, I'm going to select 2000, this with the same index, I'm going to select 2000 of those labels, the corresponding labels for these samples. Okay, so this is for my visualization alone. I'm going to train with 60,000 points. However, so I'm scaling the model, I'm applying PCA. Okay, and I'm visualizing along the first 2 principal components. Okay, so now we have 10 classes. Earlier we had just 2 classes. We have from 0 to 9 digits, right? So we have from 0 to 9. So it is pretty mashed up, but you can infer a few things from this plot. Along the first principal component, definitely 0 and 1 are well separated. Okay, this is 0, blue points are 0, and this is 1, right? So
Yeah, that makes sense. It's a circle versus a line. They're very different.
yes, circle versus a line, they're very well separated. The other digits, they seem to be mashed up around here, right? Also, what you could probably think of is like in this image, imagine that the principal component is like it it sort of is along this direction. Okay, it's somewhat horizontal. So obviously one is like sort of well separated from zero, because you know uh, along this axis, one is here, zero is somewhere here, five is like pretty spread out, but one is like pretty narrowly spread out, right? Because it's usually generally in the central part. So this axis sort of tells you the distinct, kind of helps you visualize the visualize the difference between these digits. Also, we see that say gray, what is this, 7, 9, and 4, they seem to be sort of like meshed together. And what are these points? 8, 2, 3, they seem to be again meshed together. 8, 2, 3, and 5. Does that make sense? And then 6 is sort of close to 0, right?
Roundish.
Yeah, roundish. So yeah, we get some idea of like, okay, what the data looks like. They are sort of in clusters, but not very well really distinguishable, right? If I want to draw a line, it's impossible. If I want to draw multiple decision boundaries, I would be misclassifying a lot of my digits. So I need to do some non-linear transformations. I need to add some activation. So again, so this is this is a different slice, right, along principal component 2 and 3. In this component, I see that 4 is like, oh, sorry, this, what is this, 3, number 3 is like slightly away. So when you take different slices, you will see your data from different angles, right? So in this angle, um, one is like pretty much in the center, but it's like meshed with all the other points. And in this dimension, I see that say 4 and 9 and 7, they seem to be like pretty much mixed together, but they are also separate from the other values, right? So our model will try to learn from all of this. It will do a better job than us. Okay, so this is trying to visualize a really high dimensional data in 2 or 3 dimensions for us to kind of understand what's going on. Okay, we do see that one thing we do notice, that drawing lines won't help in this case. We definitely need to add some activation, unlike the breast cancer data set, where a line was pretty good. It already had 95% accuracy. So I mean, if accuracy was our goal, then it was accurate. Okay, so the next thing we do here is we're going to load the data, and I'm going to split my data set into training and testing. So I'm training with the first 60,000 samples and its corresponding 60,000 labels, and the next is next 10,000 and the other 10, corresponding labels. So I see that 60,000 examples and 10,000 examples for testing. Now I come back to setting my hyperparameters for the model. In this case, I'm using a batch size of 16. And yeah, and again, so now I'm going to set my in features as 784 and out features as 10, right? So that is that. And then I'm going to use, so here I'm using so you should try to modify the number of layers. Here there's one input, there's a second, third, and then fourth. So there are 2 hidden layers, right? And input and output layers. So you can try modifying it. Try just having one hidden layer. Okay, or we could try how the model does without any let's just do a linear one. Model equals and then dot linear. You can try this. I think it's not probably not best to do it now. It's okay. So have I been running my notebook? I don't think so. Okay, so this gives a different representation. Strange. Very strange. Why is this happening?
What are we seeing different than?
I mean, it still looks very similar, but it's taking a different slice of the data.
That's because we're using sample, right? The
Oh,
sample
yes, yes. Yes, thank you. Yes, this is a different sample. Makes sense.
Huh.
Okay. So we're going to set the hyperparameters. Okay. And this is to load your previously trained models. And okay, I'm going to, okay. So while this is working, okay, let's wait for it to complete. It does take a lot of time because there are 60,000 samples, right? It's gonna take some time. Testing is gonna be pretty fast.
So Kyle, this is a digit recognizer, right?
Yes.
Okay.
Yeah, it's like OCR optical character recognition, like used by the post office.
Okay.
So after this, I'll just go over on some of these Python files, which the notebook depends on. I made some changes to the like dataset classes, training loops, in order to accommodate classification. So early on, we were doing regression, but the same loops also work for classification. And why they work is because I say classify equals true, and if this flag is on, then it does a slightly different calculations, right? So the algorithm is slightly different. We'll just go over what changes they are. Okay, so now I've just trained for 3 epochs, and I see my test accuracy is 97%. That's pretty good, right? 97.7%. There's still scope for improvement, right? You can improve this greatly. Try different. There are so many hyperparameters. I've not even used scheduler yet. So try scheduling. Try applying scheduler. I have used a momentum. Oh no, sorry, no. RMW, we don't use momentum. This is the initial learning rate, and if you want to add a scheduler, then you can try some of the schedulers that we discussed in lab 3. So try all of that out, and you can definitely improve this accuracy. Yeah, if you go to their website, MNIST, there's like 0.1% accuracy, right? With neural networks, you can go that far.
You mean 0.1% loss?
Oh yes. I mean say 99.9% accuracy.
Okay.
Yeah. Sorry. Okay. So here I'm saving this model, and so again, as a storing it as a dictionary, and then saving it checkpoint. Okay, saving this file as, okay, I'm saving it as best model. You can save it, I mean, it shouldn't probably be that. Okay, and if I see, let me reload. Did it is it showing up? I think this is the one. Today's 21 here. So yes, this is the model. This is the file, pth file. This is the PyTorch related file, I think. I'm not very sure, but this works when you want to reload your file. So torch.save and save as path. Okay, I'm gonna change this. Okay, and then if I want to load my model, so this is for saving it. So once you train your model, you do all your training, you save it. And if you want to like test your model, and you want to test your model with like the different models that you created, so all these lines are probably not required. These lines are not required, but let it be. What you do is you uncomment these lines, and then mm, just give the path to the uh, the file that you saved, right? If you saved it here, you just copy this and paste it here, and then you will be training on that model. Okay, and also you will have to comment out this line, comment this, just keep alternating between these two. So, okay, yeah. So also make sure that you're in evaluation mode. This should not be commented out. So in this case, uh, I'm loading a saved model. Okay, and then I'm going to test that model here. So yeah, so what I'm doing here is that this is what I did for visualizing this part 2. How do I visualize? I'm using this softmax function and argmax and things like that. So what our model basically outputs is, it's going to give me some numbers. Some, if I print out logit, okay, I haven't run this part yet. Okay, so now if I say logit, so it outputs certain numbers for each class, right? But these are not probabilities. So I can see that -12 is like is probably the largest number here. Okay, and probably this number is actually 0. But in order to convert all these numbers into probabilities, we use a function, right? You remember what it is? What um, what do we use to convert these numbers into probabilities?
It's a type of activation function.
It was covered, I think,
It's
a few classes ago. Does anyone remember?
No.
Okay, it's called a softmax function. Does that ring a bell?
yes, it was a
Okay.
lecture or two ago.
Yeah. So we have recordings on it. So you see lecture 3, we covered softmax activation function. It's best to
that like the exponential one?
Yes, exactly. We each of these values we take we sort of like e to the power of these numbers, and then we divide by the sum of e to the power of each one of them, right? So that way we get a probability, right? And once we get the probability, we want to find the argmax. So if you remember, we covered this argmax, softmax, both these things together. And that's because actually we put them together, argmax and softmax together, because we want to find the maximum probability, the index that corresponds to the maximum probability. So that's how we go about this thing. So in this case, I'm just taking 10 random examples, okay, from my test data set. And then what my model outputs is this logit, which is this number. And then I convert them into probabilities using softmax. And then I take its argmax, and that is my y hat. Okay. So I just print out what is the label for that image and what is its prediction. So I print out both of them. So, okay, we do see that there are some errors showing up here. We will see it. Okay, so 7 has been predicted correctly. 2 has been also predicted correctly. 1 looks good. 0 looks good. 4 looks good. 1 again looks good. Okay, this curly 4 also looks good. Okay, this is 9. Yes, this number. I mean, yeah, I don't blame the model, right? This is a pretty weird.
Number.
Yeah.
6.
Yes, it does look like a 6, right?
I would agree with the model.
Yeah. So the label is 5, but the prediction is 6. Okay, not bad. And then 9 has been predicted correctly. So we do see out of the 10 examples, 9 of them have been predicted right, except for 1, which is also it's a pretty good. I mean, it's a pretty good prediction. So the model works well, and we've been able to do that with a simple say feed forward network, and with a few layers, right? And so that's actually a really cool task that we've been able to do so far. So with all that we've learned, nothing out, we've not added anything else other than what we've learned so far in the class. So that's good. Any questions? Albert, Abhishek, is it okay?
It's good. Thank you.
Okay.
Yeah, Asif last went over the softmax function on June 1st. He was doing the makeup theory. He tried to make a
Yeah.
note street lamps.
So yeah, we do have the video on it. Okay. Softmax activation function, lecture 3. It's available. Also, so the next part is for you to try out the same, I mean, the same classification, but on a smaller data set. This is the low digits. So this is a 28 by 28 pixel image, right? So here we're going to use an 8 by 8 pixel image. You will load. So this is your. I mean, you can do this now, lab work, and then leave the class, right? So you can start with that now. I All you have to do is say load digits here, import from sklearn datasets, import fetch of OpenML, comma, load digits. Okay. And you can make a copy of this notebook and start editing it out. So how load digits and then do everything similar to what we've done here. Load the digits, look at its shape. So you should make sure you know the shape so that you can give the right input features and the right output features, and visualize the data set. Make some inferences before you go ahead into the model, and then train your model. So that would be your homework now. Does that sound good? Okay, I think it does.
Yes.
So yeah. So that's it for today.